Hello everyone, today I'm going to share our project on understanding the key factors that influence housing sales price and how we use machine learning to build a prediction model that is not only accurate but also reliable, stable across different data splits and interpretable. A key characteristic of housing price data is that the sale price is right skewed. So, which means a small number of high price homes stretch the distribution. If we model the raw price directly, the model can become overly influenced by large error in high price range, which often hurts the generalization. To address this, we applied a log1p transformation to sale price. This makes the target distribution closer to symmetric and stabilized variance, which typically improves the RMSE for regression. In our analysis, we also compared the distribution before and after the transformation to show why these steps help. And in the machine learning, one of the most common pitfalls is data leakage. For example, accidentally using information from test set while computing statistics, filling missing values, or deciding transformation sharehold. This can make validation results look artificially strong but performance drop in real-world use. So our role is any step that learns parameters such as imputation statistics, distribution-based sharehold, or feature transformation decisions was fit only on the training set and then applied to the test set. This makes the evaluation more trustworthy and closer to real deployment scenario. Before modeling, we build a structured set of engineered features because housing value is rarely driven by a single linear factor. Many effects come from combinations. We focus on several feature groups. First, size-related features, combining basement and above-ground living area into more complete space measures, such as total square feet. And the second is quality-size interactions. Features like overall quality times total square feet to capture how space value depends on quality. And third is time and conditional signals. Home age, time since remodel indicators for renovation status. And the fourth is amenities and functional indicators. Garage, fireplace, porch, pool, and other features that can add measurable values. The goal of feature engineering here wasn't to add more uh, variables, but to translate the real-world pricing mechanisms into structured signals that models can learn more effectively. We also treated the categorical variables carefully. Many quality-related categories, such as kitchen quality or basement quality, are ordinal. Excellent is better than good, and which good is better than fair. If one hot encodes this, we lose the ranking information. So for these variables, we use ordinal encoding to preserve the meaningful order. For other categorical features, we use one-hot encoding and ensure that training and test sets had perfectly aligned columns. Instead of committing to one model early, we benchmarked the multiple model families. We regularized linear models, rich, lasso, elastic net, stable, and interpretable. Boosting models, which includes the XGBoost, Light BGM, gradient boosting, strong at capturing nonlinearities and interactions. To evaluate performance reliably, we use k-fold cross-validation and tracked metrics such as RMSE and R-square. We also use the learning curves to diagnose whether models were overfitting or underfitting. When training performance is strong but validation performance lags, it's a sign of overfitting. And it suggests we should improve regularization, time complexity, or adopt more robust ensemble strategies. After benchmarking and diagnosis, our final approach was a stacking ensemble. The idea is that different models capture different structures in data and their errors are not perfectly correlated. By combining them, we can often improve overall accuracy and stability. To avoid the leakage in the ensemble layer, we used out-of-fold predictions. Each base model generates the predictions only on data it has not seen, and those out-of-fold predictions become inputs for second-level model. For meta-learner, we use the ridge regression because it is stable, well suited for long blending ways without overfitting. In terms of our result, the stacking ensemble delivered more stable validation performance and lower overall error, and it was less sensitive to a single. It's less sensitive to the single model. It's less sensitive to a single random trend test split. Sorry. For key drivers, ranking can vary slightly by model, but the overall patterns were consistent. Size, uh, Size-related factors are crucial, which total unusable space and living area. And overall quality and renovation level has strong influence. And third is locations and neighborhood signals carry significant predictive power. And fourth is age and remodeling status can materially shift validation. Amenities such as garage, central air, and fireplace provide measurable uplift. The practical value is that we can produce not only a price prediction, uh, but also a clear explanation of which factors are pushing in the estimate up or down, which supports pricing, purchasing, and investment decisions. Thank you.